Hello, everyone, and welcome to my weekly class summary. This is essentially just going to be me summarizing what I've learned within class for each week. And for this week, this is going to be for my Intro to Artificial Intelligence class. This is taught by Professor Kalev Kask of UCI, which is the CS 171 class, and this is in winter of 2022. And so, getting things started, first, we need to ask the question of what is AI, right? Some of you may already know what this stands for, and this stands for artificial intelligence. Artificial intelligence, essentially intelligence which we're crafting ourselves. And how are we crafting it? Through computer programs. And so within each artificial intelligence program, we can break it down into something pretty simple, in which we have an agent and we have our environment. And then the agent is going to interact with this environment by some means. And so we say that the agent takes an action onto the environment, but at the same time, our agent must also sense the environment to see where it currently is at, what actions it can take, and possibly what are the best actions to take at that moment in time. And so there are different, in terms of our environments that we can have, there are different dimensions of our environment. So environment. And so one dimension we can have is deciding whether it is a static versus a dynamic environment. Pretty much, is this environment going to remain the same, or is it going to change over time or change throughout our actions? And another dimension we have is this deterministic? Deterministic? Or is this what is called stochastic, if I'm pronouncing that right? But essentially, you can think of this was an unfamiliar term for me at first. This is like there's some sort of probability involved. Pretty much non-deterministic. Right? You can only use probability to describe things. If I flip a coin, it's either going to be heads or tails. You can't really be certain. Well, I guess you can if you get really like complex about it and say everything's known, but just to any random person, you're not going to know. You just know that it's 50% chance of heads, 50% chance of tails, and nothing else. You can't be for certain. And so another domain or another dimension of the environment is whether or not it deals with a single agent or a multi-agent. So single versus multi-agent. Put a little dash there. Single versus multi-agent. This is whether or not you're dealing with multiple AIs and interacting within the environment, or just a single one. For most simple cases that you might see going forward, we're probably going to deal with single agent cases. But I think there are maybe cases in which there's multiple. And so another domain that we can look at, or another dimension, is the how much the agent can observe within the environment. And for here, it's either going to be fully versus partially, versus there's going to be a third one here, non-observable. Is it fully observable, partially observable, or non-observable, or just unobservable? And that's basically how much basically relevant aspects of the environment are we able to get, or that the agent's able to get. And so for our next dimension, we're going to be looking at whether or not the environment is episodic versus it's sequential. That's not a B, that's a U. Sequential. And what this essentially is referring to is whether or not our current actions are going to affect future decisions. So if something is episodic, you can think of it as there's just a single episode, right? It's like a one-off type thing, and your action right now is not going to affect anything in the future. However, sequential, things being in sequence, means that the next best action might depend on what's been done or what the agent has done before or in the past. And so it's just things to consider depending on the environment. And the last dimension of an environment is whether or not it is discrete versus continuous. And so if something is discrete, there is a finite number of states, or not even a finite, but just there are clear and definite states in which you might jump from one state to another. But continuous, everything is almost spread out. You can think of it as maybe a number line in which discrete components of this number line would just be like the integers, like 1, 2, 3, right? You're just jumping from component to component. But continuous, right, might be just the entire number line itself, right? It's hard to describe what's something you can jump to next when you have infinitely many numbers inside of this number line, right? Because you have 0, but what comes after 0? Like 0.00001, right? You can put more zeros before that, but there's kind of just a smooth and continuous flow of numbers, of increasing numbers that you can have. And so now moving on, one architecture of intelligence that we were introduced to this week would be search. And so we can say architecture of intelligence is search. This is one of many, right? If you've heard of AI before, like which probably most of you have, you may have heard of like machine learning, or stuff such as knowledge representation, and maybe AI within like video games and stuff like that, and all that. They're all branches of AI, and search is included. And so we're going to start off with search, and as we go along throughout the class, we're going to learn about more architectures for intelligence. And so now jumping to search, first we need to define like what a search problem is. And so a search problem, essentially, at its core, you might think of it like, we've all searched for stuff before. All we're trying to do is we're trying to find from our given current position, basically where we start, we're trying to find a path towards the goal, or where we're trying to get to. But in terms of search for artificial intelligence, we want to get there in the most optimal way. And so search is an optimal, or I should say, not just an optimal, but finding that optimal path. Finding an optimal path to solve a problem. And so within each search problem, there are two things. The first thing is a state space, which this is just the set of environmental states. Oops. Kind of squeezing it there. Let me actually skip this over. Environmental states. And within each of these, we can have our start or initial state, as well as our, I'll say that this is the end, or otherwise known as the goal state. Right? We obviously, in order for us to have a search type problem, we need to know where we're starting, right? And similar to that, we also need to know where we're ending. And we need to know kind of what states we can go to in between from the start to the finish. And the second aspect of a search problem is we need our set of actions that we can take, in which we can call our state actions. These, as you may have guessed, these are our set of actions we can take at a given state. And so let me actually scoot this over here, grab this, slide this over here. There we go. And to describe our state actions, there are two things to consider. One is the transition model, which is describing kind of based off a certain action a certain state that you're currently at. From a certain state you're currently at, what actions can you take, right? And the second thing are basically, for each of those actions that you can take, how much do they cost? Which is an action cost function. So we need something to describe what actions we can take at a state and also how much they cost. And so what we can do, zooming out here, is we can put both of these terms together and get what is referred to as a state space graph, which might look like any other graph that you're familiar with, right? And so I can write something like this, in which we have state A, B, C, D. So from A, I'm just saying I can go from A, I can go to C and B, and then from B, let's say I can self-loop to myself, and I can also go to C, and from C, I can self-loop, and I can also go, let's say I can also go to B, and I can also go to D. And then let's just leave it simple and set it right there. And so this would be an example of our state space graph, right? In which for this graph here, our states would be A, B, C, and D. And our actions actually, hopefully you may have caught this. This isn't complete because we don't really have we're missing our action cost function, right? We need to specify for each of these how much each action costs, and don't worry about the start and end just yet. We won't need those just yet. We'll define those afterwards once we actually kind of create a search problem for the state space graph. And so let's just say from A to C, it costs, let's say maybe 8 points. A to B costs 2 points. B to C, I'll just put random numbers here, just putting them arbitrarily. Say a loop is, let's just say 1. Each loop is 1. From here, it's say 5. Okay, and then we have also our actions we can take, which is a bit more complex to represent, but we can represent this as a 2D array, or essentially just a matrix, in which we have A, B, C, D, and I can cut this to, once I finish, A, B, C, D. All right, so I finished making our 2D array, or our matrix representing our state actions, where it's kind of a 2-in-1, in which we have our transition model and our action cost function, both in here, where we'll define our transition model to be that you can move from let's see, this is the row R, and this is the column. I'll just call this row and column, in which each value within this matrix describes you moving from a row to a column state. And you can make that move if there's a non-zero action cost function associated with it. So for instance, moving from A to A, we cannot move from A to A, essentially just self loop, because there's a cost of 0 for that. However, if we wanted to move from A to B, then we could, and it would cost us 2 points to do so. And that is represented here. From A to B, we can move there, and it costs us 2 points. And this is not symmetric, because if I wanted to move from B to A, this is actually 0 points. So moving from B to A, I can't do that, right? Because I have nothing defining that. And you can see for every value here on this matrix, it's going to basically allow you to derive our state space graph. And so, yeah, for the state space graph, let me just also note that we don't need to define our start and our end states here, because this is just basically referring to our problem that we have, or our general environment that we have. And then for the specific search problem, that's where you might define different start and end states, right? Because I can say that, oh, I'm going to start here and I want to end here. But I can also just say, actually, for an entirely different problem, I want to start here on B, and I actually want to end here on A. And so this isn't a formal definition. This is something that just helps me remember. But you can think of the state space graph as the entire environment that you have, and then the different possible start and end states as being specific problems, specific search problems within that environment. And I should also note too that you can have more than one end state. So I can, but you can only have one start state. So I can only start in one place, but I can say, oh, I want to end on either A or end on B, whichever one I either find first or find like to be more optimal to go to first. And you just care about getting just to one of them, not to both. And so now, actually before we move on, I just want to note that when building a state space graph for any type of like problem, it's important to remember that to build a state space graph, we're essentially just creating a simplified model of reality, right? Which we can describe by the term abstraction. We want to create something that's abstract from reality so that it makes it much simpler, much easier for us to generate a state space graph for that, because something like this is pretty abstract in the sense of, like, we can say that this represents I don't know, traffic flow data in which each of these action cost functions are maybe roads that you can go on, and for each of those roads, each of these values is a specific time it would take you to go there. So if I want to go from A to B, it'll take me 2 minutes. And if I take some, I don't know, roundabout road to go from B to B, it'll just take me 1 minute. But if I go from B to C, it'll take me 3 minutes. And so you can see, maybe for this problem here, if my start was at A, and I said I wanted to get to my friend's house that's at C, now something that's pretty obvious to see is just a straight path down. So it's like, okay, cool. I found that path. We're good to go. However, if we want to find the most optimal path, and I want to give the extra parameter of saying I want to get to my friend's house, but as soon as possible, in that case, then I would take into account this road here, but I would also need to search through other roads and say, okay, what happens if I take this roundabout road, maybe from A to B, which only takes me 2 minutes, and then from B to C, which only takes 3 minutes. Now I cannot go on this road and go the roundabout method, and instead of it taking 8 minutes, it now takes me 2 plus 5, which is my bad, 2 plus 3, which is 5 minutes, right? And so now I've gotten to my friend's house 3 minutes sooner than if I just went the straight line path from A to C, right? And so now we need kind of methods and algorithms for us to solve these type of search problems. So now moving on to looking at specific, like, search algorithms or search methods that we have for these problems. We have different search methods. There are two classes of methods that we can look at. And one of them is the uninformed search, and another one is the informed search. Now for week 1, we're just going to be looking at the uninformed search, and for week 2, we will be looking at the informed search, which is the more, I guess you can consider, the more smart search, because you're using information and stuff such as like guesstimates, known as heuristics, to determine what is the better path to look down first, rather than searching just kind of almost randomly, which is in our uninformed search. Because in uninformed search, as the name implies, we really have no information. We are uninformed about how close we are to the goal from where we are currently at, right? Whereas informed search, it tells us a general approximation of how close we are to the goal from where we are at, and so we can use that information to make the search easier and quicker. But we'll just focus on the uninformed search for this week. And so there are, what I'll say, like, there are 3 main uninformed search that we look through, and the first is going to be breadth first search, abbreviated as BFS. Another one is the depth first search, abbreviate it as DFS. And the last is the Uniform Cost Search, which we can abbreviate as UCS. Put parentheses around the abbreviations. And we'll look through each of these three through a simple example, so that you can give a basic idea of these. So you actually may have seen these algorithms within, if you take in a data structures and algorithms course, they'll usually show the breadth first search and depth first search algorithms, as well as the uniform cost search. But depending on your class, I don't think they'll refer it in that way. But we'll see what exactly this algorithm is once we get to it. But let's first focus on breadth first search. So now let's create a state space graph for us to show us going through each of these search methods here. And so I'm going to create a state space graph that isn't too complex, but can show us maybe the differences within these methods. Maybe going down here. And let's do something like this and this and that. And just one more just for good measure. And so we're going to give each of these its own, each of these states its own name. We'll say this is A, B, C, D, E, F, G, and H. And so I'm going to say that this A here is our start, and this H here is our goal. And so let me actually slide this state space graph over to the left. And so now what we're going to do is we're going to first go through the breadth first search. And so just a general overview first, just to give us maybe a better idea about how this is going to work, is breadth first search. What you're essentially doing is you're looking at each neighbor first. And so if I'm starting here, I want to first look here and here, and then from this neighbor here, I want to look here and here. And then if I see that I don't have the goal, then I need to look at this neighbor now and look at just here. And so now once I finish that, then I look at the neighbors of those neighbors, which would just be D, which I would look here. Okay, that's not the goal. Here, I look at the neighbors here, and then at now, oh yeah, it would just be that. And so now I look at the neighbors of those neighbors of those neighbors, and you keep going down through here until you find the goal. If you want to see this as basically what you might find in maybe like textbooks, and what they'll show you is like you're kind of taking breaths, which is why it's called breadth first search, in which you first start at your start state, and then you just make this bigger circle encapsulating all of the neighbors. And then if you see that, okay, the goal is not here, then you look at the neighbors of your bigger circle and see that you have this here. And you can see as we're making these circles, it's almost like if you can treat this big purple circle as a single state in which the neighbors of this node are just the outwards arrows going in here. And so that's why now here, the next bigger circle would only take up G, state G, which is not what we're looking for just yet. And then the bigger circle would finally take up our goal state. And then we finally found H by doing all these different breaths. But how this is going to look more algorithmically is we're going to have a queue in which we want stuff coming in from the back, exiting through the front. And so what we're going to do is we're going to start with our start state, A in this case. And then once we see that, okay, our start state before putting it into the queue is not a goal state, what we then do is we expand the node. And so this is going to be the expand order here, in which we're going to first expand A to get both of its neighbors. And so we're going to, or not, I shouldn't say both, we're going to get just pretty much all the neighbors of A, in which in this case are B and C. And the way you put them into the queue really depends on your implementation, but we'll just say we're putting them in an alphabetical order. And so we would first just put in B, then put in C. And so once we've expanded A, we want to make sure we remove it from the queue. And then now we shift this these two states forward. And so now what we're going to do is we're going to expand B, which allows us to erase B, which allows C to shift over. And we see once we expand B here, and that would give us D and E. And so we can put this in the queue in alphabetical order, D then E. And so next thing to do is then to get C out of the queue, and actually to visualize it more. This might make it a little bit better. To visualize it more, let me grab C directly from the queue. When we take it out of the queue, we now expand C, which then allows us to get C's neighbors, which is just E. And now everything shifts up one. Next thing to expand would be D. And if we expand D, we'll get G. So we put that into the queue here. And slide this forward. And then from here, we're going to expand E. Put this here. Slide this forward. And from E we get, it's alphabetical order, A, B, C, D, F, G. Yeah, so we would have to put in F and then G in the queue. And we can see we're going to expand E again, basically because it's just coming directly from our queue. And so the neighbors of E are going to be F and G. So they go into here. Next thing to expand is going to be G. And once we expand G, we can see that the neighbor of G is H, which before putting it into the queue, this is important, I was kind of skipping over this, which is kind of bad, but I'm just mentioning it now. Before putting it into the queue, we check to see if it's a goal state. So H is like, right here, it's like, I'm about to put it into here, but first let me check if it's a goal. Basically, that's like the condition to first that you must first pass to enter into the queue. But if this is true, then we just exit from putting this into the queue and we found our path. Right? And so instead of H going into the queue, now H goes into our solution. And putting H within the expansion or not, I don't think you would, but I may be wrong about that. But what does matter is that we end once we found this, so we don't need to expand F and G within here first, because if we didn't have this check, we can see how it'd be a little bit inefficient, because we're gonna have to expand a bunch, and then we'll encounter H once we take it out of the queue. So that's why we want to have this check first, and this is true for H. Okay, jumping in here. I don't know how to make a smooth cut here. I just needed to check back at my class notes to make sure everything I was saying is correct. And so one thing I want to note is that yes, in here we would check if this goal is, or if this state is a goal, and if that's the case, true, it would still be within our expansion order here. And so this would be at the end of here. And in terms of building up our, basically the path, the path, I guess we'll call it the path order, the path that we travel down, is we would first say, okay, well, we reached H at the end, which is our goal. And so what was the state that we expanded to get to H, right? Because like in the case for G, we expanded D to get the G, but we also expanded E to get the G. And so in terms of the implementation, each of these would have like the parent that expands it. And so from H, we had G, which expanded that. And for G, what was expanded into G here. And so this G here, we can see from our expansion order from H, we expanded into G. And the important thing to note is you might say that, oh, well, okay, in our expansion order, E is right here, and that expand, and E, when we expand it, expands into G. But remember, we have a Q here, and so we want the last state that in our expansion order that expands into G, and that last state going from and that last state looking from, I guess, the back to the front will be that state that expanded into G. So we'll look at here, we'll say, okay, E expands into G, so we'll just say, okay, this is possibly it. Another E expands into G, okay, this is possibly it. D expands into G, okay, this is possibly it, might be D. C, it's not possible. B is not possible. A is not possible. Okay, and so the last one we found was D here. And so now the next state in here was D. And so now from D, let's look at, okay, what expands into D? And so we can start here within our expansion order, and let's look at C. C does not expand into D. Nope. Does B expand into D? Nope. Does A expand into D? Yes, it does. A. And we can see here A is just our start node, and so from there we're good. And now this would be our path order that we travel down. And so in terms of breadth first search, the path that we would generate to go down would be from A to B, B to D, D to G, and G to H. And now there's one important thing I want to note here. Notice how I actually forgot to do this, which is my bad. But I didn't put down the action cost function, right? I didn't put down anything. But there's two things I'll note. One is usually if you see the state space graph and there's nothing written down, it's always assumed that the cost of each of these are just 1. They're all the same and they're all 1. And the second thing is that for breadth first search, it's actually nowhere within here, which you can see it's a little bit maybe easier to see because I didn't have to use anything in here in terms of like the cost. Nowhere within breadth first search am I using the action cost, right? So this can be like 8, 2, 3, 7, 1, 5, 9, 10, and let's not make that 11. We'll just make that 1. Yeah. And then you can see here that what's it called? This will still generate the same path. And so, yeah, this is breadth first search. And so now next we'll move on to depth first search and see what that looks like. And so let me clear up the screen, and this time I'll write the action cost function for each arrow here within our state space graph. And let me jump to that real quick. And all right, okay. So I've cleared the board. You may have noticed the action cost function for each of these actions is different because I had to erase them and I forgot what I wrote, but it's not going to matter because for depth first search, it's going to be the same case as breadth first search, in which we're not taking into account the actual cost of each function. And so, similar to how we looked at breadth first search, we saw maybe like a higher level way to think about it, and then we got more and more detail. For depth first search, we'll do the same. And so for depth first search, what we're essentially going to be looking at is we're going to be essentially going into a deep dive into the farthest we can into a certain path before we jump back out and look at other means to go about it. And so if we were just to pretend that this state is not the goal here, and we wanted to search every node, what depth first search would do is we would first go down, because if we're considering which path to go down first, we'll just consider like go down the one that occurs if the state, my bad, I'm saying that wrong. Go down the state first, which comes first in alphabetical order, and so B comes before C, and so we'll go down B first, and then from B, then we go down B even more, and so we decide to go down D or E. Well, D comes first, so we go down D. From D, we can only go to G. From G, we can only go to H. And let's just say H was not the goal we were looking for. And so we essentially backtrack and see, is there anywhere else we can go from G? Nope. Backtrack. Nowhere we can go from D. Backtrack. From B, now we can go to E here. And from E, we can go to, wait, there's A, B, C, D, E, F, G. Aha. Okay, it'll go to F first, because F comes before G. It sees that nothing's after F, so we backtrack. Next, from here, we can go to G. And then from G, we go to H. And then from here, we see we can go nowhere, so we backtrack again. From E, there's nowhere else we can go that we've already gone before, so we backtrack. From B, nowhere else we can go, so we backtrack to A. And from A, we go to C. And C, we go down one to E. And from E, we go to F first, and nowhere to go from F, so we backtrack. From E, go to G. From G, we go to H. Nowhere else to go, backtrack. 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 And we're back at A with nowhere else to go, and so we stop. And so in terms of what we would expect to happen for this algorithm on this state space graph, you can see it's going to be a pretty easy search, because we're just going to go down the deepest node first, and we're going to get to H, and H is our goal. And so we expect basically our order of expansion to just be right away, like the path, like the most optimal path. We're not going to need to look anywhere else. And for this example, you might think in that case, okay, well, depth first search seems a little bit better than breadth first search. But there are some cases where that is true, because you're not expanding out a lot more, but there's some stuff you will need to consider, which we'll look at afterwards. But let's run through this, right? So looking more in depth about how to implement depth first search, for breadth first search, we use a queue. And so now the question is, okay, well, what data structure can we use for depth first search? And in depth first search, we can use what's referred to as a stack. And so in the stack, it has a first in, last out structure, in which the first thing that comes in is going to be the last thing that we're going to take out. And so getting these nodes in a similar fashion. And actually, I forgot one thing, which we'll see when it comes up. But first off, we start from A. So we have node A. Node A, we put into the stack here. And then we see that there's nothing else to put in, right? Because the first thing is obviously like, we only just have one starting point. And so we have our expansion order again. In which now what we're going to do is we take out the state from the top of the stack, and we expand A. And so now here's the thing. We're going to still put in nodes in alphabetical order. In the queue, it worked out where the first thing we put in is the first thing we take out. And so if we put in B first, we would take out B next. But in the stack, if we do that, we put in B, then we put in C. You'll see that the next thing we're going to take out in the stack is going to be C. And so that's why I was actually wrong, in which when I said from A, we're going to go from B to D, and from G and H, and you can see in that fashion, then that first search would work out a little bit better. But you can see this is actually not the case here, because we're going to actually want to go to C first based off our implementation. But you can always change this. If you wanted to keep it the way from before, then you can just define that you're putting in the states into the stack opposite of alphabetical order, in reverse alphabetical order. And so in reverse alphabetical order, you would put in C first, and then you would put in B. And so then the first thing you expand and take out would be B. But let's just keep the way we put these states into the data structure consistent throughout each of these trials. And so we're going to put in B first. It comes first alphabetically. Then we put in C. And so we see we have no other neighbors to expand from A. And so in that case, we take out the top of the stack here, which is C. And so now that we've traversed along C here, from C we get the neighbors of C, which is just E, and we put that into the stack. And now there's no other neighbors of C to expand and put into the stack. And so now we take out E from the stack, expand it, and we see now the neighbors of E are going to be F and G. Since F comes before G alphabetically, put F in here, and we put G in here. And so let me draw this arrow here first. And so now we have no other states to expand to from E. And so we take out the top node from the stack here, which is G. And so now from E we go to G. And then we see the neighbor of G is H. And now, again, another important thing to note is before putting H into the stack here, we need to check for this is happening for every single state. So when I was saying basically put F into the stack or put B into the stack, what I should really say is F a goal state? No. Okay, put it into the stack. Is B a goal state? No. Okay, put it into the stack. But is H a goal state? Yes. And so if it is true, then we grab H, put it onto the end of our expansion. And then now in terms of getting our path order, now for here the path order is going to be pretty, I guess, trivial. From getting the path order from the expansion order is going to be pretty trivial, in that we see that the path order is going to be the same as the expansion order, which is going to be A, C, E, G, H, which doesn't feel satisfying, because it's like, well, what about these cases in which the expansion order is not equal to the path order? What would we do? And so we can actually look at that. And instead of this being F here, let's just say this was, I don't know, I. And so now, jumping back to what we had previously, let's jump back here. And so before going to G would be in the stack, but now instead of F, we'll make this I. And so when we expanded E, now we had I and G. And so now G comes before I, so G goes in first, I goes in next. And now there's nothing else to expand from E. And then from E, we expand to I here, which would bring us to the right here. And from I, there's nothing else to expand. And so we add nothing to the stack. Simple as that. And so then this whole idea of like backtracking, what I referred to earlier, is just pretty much seen here. It's just pretty much adding nothing to the stack and then taking out the next thing in the stack. And so now what we would do is, since we added nothing to the stack, we take out the top of the stack, which now it's G. So now we take out G from the stack. And then when we expand G, we see that we have H. And now, remember, we still have that is goal state. And so before adding H into the stack, we say, oh, it is actually a goal state. If it's true, we just shuffle it off to the side. And by doing so, we'll just put it at the end of our expansion order. And so now this is a little bit more interesting case of okay, now what is our path order going to be here? It's a little bit hard to see at first, but what we can actually see from depth first search is that we're actually trying to take a straight shot directly from the start to the goal. And so given any expansion order, all you're going to really need to do is get the expansion, get the node that expands into the current node that you're looking at, if you were to go from the end to the start. So I guess an example would better show this. Since say, for instance, if there was some way to expand this this state space search such that I go from like B and also go to E, and so like I would have two E's in here, you can see that like this would never be the case, because since E gets us directly to the goal, then I would never have to expand this state twice, because if I do expand it twice, it means that goal does not that the state does not lead me to the goal at all, right? Because if I expanded to E before, then it would have already like, say if I expanded to E here, but I have E over here, then if I already got to E before and E is part of the solution, I should have already gone to G and H right away, because depth first search just keeps going down, 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 down. Right? And so in that case, all I'm going to need to look for is the first instance of a node that is what we can treat as like the parent of the node that you're at when you end on the goal here. And so it might be a bit confusing, so let me just draw this out. So we ended at H here, right? And so what's the parent of H? At what state, when expanded, gives me gives me H? And in this case, in our expansion order, we look to the left, it would be G. So as soon as we see G, we just need to write that down. And so now what state, when expanded, gives me G? So let's look to the left. Can't be I, because I expanded gets nothing. Look to the left again. E when expanded gives me G. So write that down. And now from E, let's look at the parent of E. So let's look at the left in this expansion order. We see C when expanded gives me E. So I'm gonna write down C. And we can keep going. What state when expanded gives me C? And this is A. And so A is right here. And we see A is our start. And so then our path order here would be A to C to E to G and to H. So let me write that in red. Just like that. And so now, before moving on, there's one thing to consider, right? Because now looking at this, you might see, oh, hey, well, I mean, we're not considering any of like these nodes, right? So depth first search, it can be pretty good, right? But not entirely, right? Because there are some circumstances that you would have to account for. One of which would be like fairly common, would be a self loop, right? Because as soon as I do something like put like a self loop at C, or even let's make it like a self loop at I here, you can see that. Let me actually clear the screen a bit. Let me go back. Actually, let me go back all the way to when we were putting an I into here. Just like that. So if we had a self loop at I, then what would actually be happening is we'd say, okay, let's take out I, we expand I, and what's the parent of, or what node when expanded, what are the nodes that we get to when we expand I? Well, it's I, and that's just it. So let's put I into the stack. And you can probably already see the problem with this, because then now we expand the top node in the stack, which is I, and expanding I gives me I. And so then I put I into the stack, and now you'll see that all what's going to happen is that this is just going to keep giving me I in the expansion order, and this will never stop. And so when implementing a depth first search, what you need to do is you need to account for is in like an is in loop function that can detect when you are in a loop, and it will just not put that state in the stack. And so let me actually, instead of putting it there, I should put it here. It's kind of like another condition on your stack. So you have like the is goal function, where if it's true, it kicks it out of the stack. And at the same time, you can have the is loop function, where it can see if you keep getting the same state, or if you notice that you're in this loop, then if this is true, then you'll also just kick this state out of the stack, and you won't consider it to be part of the stack. And in terms of the expansion order, if the is goal is true, we expand, and if the is loop is true, we just do nothing. Right? We're treating it as if we don't even have this self loop in the first place, and then that can help out with that. But now another problem that can happen here is that what if say instead of there being a self loop here, what if I just have an infinite number of states? I just have state, 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 and it just keeps going on forever. Right? It's like, what can you do about that, right? Because you can have state space graphs that are like this. It might not be as common, but they can happen. And so there isn't really any good way around this, right? In which because of something like this can occur, what we would say is that the depth first search search method is not complete, right? Because by using depth first search, if a solution exists, depending on the search state graph, you're not guaranteed to get your solution. Whereas for breadth first search, yeah, it might take a little bit longer, but you're still going to be able to get to the goal, right? Because even if you have this infinite number of states here, then the breadth first search will just kind of do this circling method, which do bigger and bigger circles. As you can see here, all we're doing is just circling just one more state within this within this like infinite sequence over here. But you can see eventually we're going to circle that goal there, in which that's being blocked by that. So yeah, that's why breadth first search would be a complete search method, whereas depth first search is not. But depth first search is a little bit faster. And so before moving on to the uniform cost, there can maybe be a possible solution where it's like, okay, well, how do we make depth first search a little bit better? And the way we do that is by doing what is referred to as an iterative depth first search. So I'll put a little star here, and I'll say this is an iterative. I'll put DFS. Iterative depth first search, in which all that's doing is you're essentially just iterating through a maximum depth that you can have for your depth first search. And so what that would actually look like, I won't go too much into depth of it, but just doing, I guess doing just a quick example. Actually, let's not do a quick example. I'm gonna have the timestamps down below, and so if you want to pass this, it's completely fine. And you can move on to uniform cost search. But I'm just gonna go through this. I'm gonna go through this. And so let's say we have now this new state space in which we have a self loop at C and an infinite sequence of nodes at I. So in iterative depth first search, how we would actually go about it. So this is going to be our expansion, and this is going to be our expansion order. And so from the start, what we would first do is we would have our I guess maximum depth iterator, in which we'll call this L. I'm gonna put this in a box over here. So first L is just gonna be equal to 0. And so I'd first start and I would say, okay, start at the start state. And so we have A here, in which A is going to be expanded, and A gets expanded to be B and C. And so C, oops, my bad. It's B goes in first. And then C. And we'll have some count here. I'll put count D for the count of the depth. I'll just call it count depth. So we expanded A, so now this is, so once we expanded A, this is now at 0, right? And then once we, or I should say, okay, so we got A, we expanded A, we were at 0, and then so we increase this to 1 once we've expanded A. We'll see this more in detail for later expansions. But now, in order for me to expand C, the count depth must be less than or equal to our maximum depth L. But since it is not at this current point in time, then we stop. And we restart. And so by restarting, we take out everything from the stack. We still keep everything in the expansion order. But now we reset this to 0. And we start again from square one. So we go A here, put this in the stack. And from here the count depth is 0. So since 0 is less than or equal to 0, which is, whoops, I forgot to do one last thing. now that we've restarted, now we iterate through L by, or we increase L by 1. And so now we start again, and where we put A within the stack. Now we see that the count depth is 0, which is less than or equal to 1. So we can take out A from the stack, put it in our expansion order. Note how we have these two A's here, because the expansion order won't be reset at all. And now that we've expanded A, now our count depth is 1. And so when we expanded A, we have C and B, where B will go in first, C will go in next. And then we see that our count depth, 1, is less than or equal to 1. And so that's perfect. We can expand C. And by expanding C, now I should note that for here, count depth was still 1. It's going to be important to note for us to remember later. And so from C, I can see that when expanding C, I can get E. So E goes into the stack. But now the count depth is 2. And so for E, the count depth is 2. And so in order for us to expand E, L must be less than or equal to 2. 2 must be less than or equal to L. But since L is 1, we cannot expand E. And so in essence, we just delete it. And so now we can see, now if we take that out from the stack, our count depth is back to 1 because of the 1 I noted down here in B. And so what I'll do here is now expand B. And by expanding B, I'm checking out its neighboring nodes, which are D and E. And so we would put D in here and E in here. And I should note for these two nodes, they're at depth 2. And so the count depth for these two would be at 2. And so if I try to expand these nodes, I can't because they're at a depth 2 already, and I can only expand things that are less than or equal to L here. And so instead of expanding this E, I just delete it. And same thing for this D, instead of expanding it, I just delete it. And now we can see here that we're at an empty stack. And so we can see here that that once we reach this empty stack, now we increase L by 2 and we start over. And so instead of having this count depth here, I think that's a little bit confusing. I'm just going to put the associated number of the depth next to that next to that state. So we have A, comma 0. It has a depth of 0. So that goes in here. And now we can see that 0 is less than or equal to 2. And so we'll take out A, have it here. And when expanding A, I'll make it a little bit quicker. I'll just write it into the stack. We'll first put B in here, then put C in here, in which these both have a depth of 1. And so then we're going to expand C because C has a depth of 1. 1 is less than or equal to 2, which is our value for L. And for C here, we're just going to get E, and E has a depth of 2. And we can now expand E because 2 is less than or equal to 2. which is the depth of E. And if we expand E, we would get G, which has a value of 3. And now we see that we cannot expand G because 3 is not less than or equal to 2. And so instead of expanding it, we just take it out of the stack, which moves us on to B. And B has a value of 1, which is less than or equal to L. And so we would expand that. And by expanding that, we see that the neighbors of B are D and E. So D has a value of 2, and E has a value of 2. And so E, we can expand. And if we expand E, my bad, for that previous E, I missed the I. So that's my bad, but you guys would have seen that the I would have a value of 3, and we wouldn't have been able to expand that, and we would have just taken it out of the stack. But you can see it right now because we just expanded another E, and for that E, now we have we first do I comes after G, so we would first put in G here, which is 3, and I, which is 3. And we see that I3, we would expand it, but it has a value of 3, a depth of 3, I should say, which is not less than or equal to 2, which 2 is the value of L. So we delete that. For G here, we have 3, but 3 is not less than or equal to 2 over here. And so instead of expanding G, we delete it. And that gives us D here. And so we can expand D. And so when expanding D, the only thing we get is G, which has a value of 3. And now we can see we can't expand G because it has a depth of 3, but we want everything to be less than or equal to L, which right now is 2. And so now we remove that, and now boom, our stack is empty, but we still have not reached the goal state. And so therefore, we must now increase the value from 2 to 3. We must increase our max depth value from 2 to 3. And so now what you'll see, you'll see here that this was L is equal to 1. I'm gonna do like a little shortcut right here just to make it easier. Right here is L is equal to 0. And for this ACB, this is L is equal to 1. And now this ACEBD, L is equal to 2. And so you can see how... Nope, I'm wrong. I was gonna say how this first sequence is going to be this first sequence, but that is not the case because depth first search does not work like that. You're going to go down the deepest depth first. And so actually, there's really no shortcut to this. You just have to kind of almost power through. And so at the very least, we know that you'll always start off by expanding the start state node. And so A would go into here, which I have a value of 0. 0 is less than 3 now, or less than or equal to 3. And so we're going to expand A. And I think by how depth first search works, just regular depth first search works, we'll be able to get to the goal state like right away, so this won't take too much longer. And so by expanding A, we're going to get first put B in there that has a depth of 1, and C in there that has a depth of 1. And so we expand the top, which is C, and we get the neighbor of C, which is going to be E, which has a depth of 2. And since E is at the top, we're going to expand that. And by expanding E, we can get G with a depth of 3 and I with a depth of 3. And just because we're going to need it, let's say A, B, C, D, E, F, G, H, I, this is going to be J. I'll write this bigger. State J there. We're not going to need the names of the state of those other states. Because what we're going to need to do is we see that I is at the top of this stack. So I gets expanded, which then the only neighbor of I is going to be J with a depth of 4. But now, I should zoom out a bit. But now we see that J with depth of 4 is not less than or equal to 3 anymore. And so instead of expanding J, I'm just going to take it out of the stack. Which leaves us to G. And for G, G has a depth of 3. And since 3 is less than or equal to 3, we expand it. And now by expanding it, we're going to have H that has a value of 4. Now here's a little bit of a weird part. Because H has a value of 4, and we won't necessarily be able to expand it, but how are we defining like our stack before, right? Like our like stack check state, or our stack like checking function. I don't know a good way to describe it, but the one where we were saying is a goal state, right? What did we say about this? We said that if this is true, then we expand, and also we're finished, right? And so when we put H4 into the stack, we first check, is H a goal state? Well, actually it is, so it's true. So we're going to actually now expand H. Let me get rid of that 4 depth, we don't care about that, into here. And now we finished, and we don't need to check anything else, which is kind of weird, right? Because H right here, this has a depth equals to 4. But right here on the top left, L is equal to 3. So how can we possibly expand something that has a depth of 4 when our max depth that we can expand is anything that's less than or equal to 3? And the reasoning for that is because of this function here to check if a goal is a state before we put it into the stack, right? Because we're still putting in stuff that has a depth of L plus 1 into the stack. We just don't expand that. But since by the definition of this is goal state, if that is true, we just put it at the end of the expansion order. Then that's how it gets there in the first place, which is a bit weird. But it's almost just kind of like our ending, right? We don't want to have to loop through a whole nother piece of this with like L is equal to 3, and then loop to L is equal to 4, and then finally get that goal state, right? This cuts down a lot of computation time, and so that's the reason why we want to check for that goal state beforehand. And so yeah, this is this right here is the L is equal to 3 plus goal is found. And you can see with something like this, I just completely forgot that that C had a self loop here that I was not accounting for. But I'll tell you this much: the expansion order is entirely the same, right? Whether or not this loop here is here or not, all that would happen is basically once I put C back in here, I would just take it out of the stack, or I wouldn't even put it into the stack in the first place because I would notice that it's a self loop. So that's what the whole purpose of like having that function to check if something's like looping for the depth first search or not is. But just note that, yeah, the expansion order will be the same if we have a self loop here or not. I was forgetting to account for it. That's my bad. But yeah, the expansion order will still be the same with this self loop. And so now this brings us to the problem of, okay, now what's the path order from here? Right? Because this is a lot to consider for the expansion order. Well, let's use our same method. Of course, we're ending at h, right? And actually, I mean, if you look at the expansion order, we're not really going to consider the L is equal to 0, 1, or L is equal to 2 path, right? Because those are just different depths, right? It's just more, it's just basically more ways to expand the node, but it allows us to have this complete search method in which for iterative depth first search, if there's a goal that exists, you are always guaranteed to find it, because you're doing this iterative depth first search in which you're constantly increasing the max depth by 1, which allows you to avoid these infinite sequences. And also, if you need to have your function to check if something's a self loop within here, so that you don't run into that. But with those two conditions accounted for, then you now have something that's complete. But you can see here that we're only really going to need to take into account our last L value. And so from H here, it's going to be the same exact thing as the depth first search that we first went through, in which you will never expand a node twice, because if you do, like in this case, you will not find the goal. Unless if actually I might have been wrong about that. Because if say for this case, if E pointed to D and D was the goal, then no, but then you would have already found it at B. Yeah, I think it's just it's something you should account for. But as of right now, we can this method still works, in which you can just start from H, and from H you can see that, okay, from H you see the parent of H is G, and so you have G here. From G, the parents of G are D and E, and so we have I here, and we have E here, and so we have E, so we can put that here. And from E, we have the parents of E being C and B, which we have C. We're just only taking into account the first one that we see, because we won't get any other parent. We'll only just have one parent within each of these. And then from C, the parent of C is A, which is to the left here. So we have A here. And our path order here would be A to C to E to G to H, which you'll see it's the same exact thing as depth first search, but it allows you to avoid this infinite sequence where just doing regular depth first search would get stuck in this infinite sequence, but iterative depth first search will not. So that's the only difference. And it's just a little bit more expansions in order for you to get that completeness. But yeah, let's move on to the final uninformed search method, which is going to be the uniform cost search. All right, now let's jump to the uniform cost search. And so now, as the name may imply, for this search method, you will now be using the action costs for each state, and where the uniform comes in from, this isn't really in a, like a formal or official type definition, but just helps me remember, is that we're putting in a uniform weight on each of these costs, where each cost we're just taking into account just the costs. We're not saying that certain cost is like should take more priority or cost more than something else. It's basically just going to be 8 is greater than 2 because 8 is greater than 2. Nothing else. We're not putting any weights on them. And so with that, let's get into it. So there's not really, I guess, a higher level, like, better way to think about this. Like, I guess there is, but it's just more through thought, where it's like it's more intuitive, right? Where I'm basically telling you, like, what is the least cost path going from A to H. And all you're really going to do is you're going to want to first kind of look through the lowest cost states first. So you have 2 here, and then you have 2 plus 5, which is 7, which 7 here is good. And then you have 7 plus, or I guess you wouldn't really take into account F, but you will in the algorithm. But 7 plus 7 here is 14, so you have 14 when you get to here. But then what you may ask then is like, okay, well, what happens if I go down like this left path and I get there? Like, before continuing, like I see now I have like an 8 here, which is better than this 14. I have this now 8 plus 5 here, which is 13 here. Okay, but now actually when I go, this 13 plus 9 is not better than 14, so this 14 is better. But you may actually also say, okay, from 8 here, we have plus 3 here, which would be 11. But if I went from 2 plus 5, which is 7, 7 is better than that 11. So yeah, okay, this 14 is the best we have, and then 14 plus 1 is 15. And you can see the best way to get here would be to go through this same this path here, and it would cost 15 points. And remember, we're trying to get from the start to the end with the lowest amount of points. If you want to think about it this way, a way I like to tell people is that you can think of, instead of points, as it costs this amount of money to travel down these roads. Like, you can think of it how that all these are like toll roads, and each of these costs a certain amount of money, and I want to get from the start to the end and spend the least amount of money possible. And so how are we going to do it? So the data structure we can use for this search method is actually going to be a priority queue. Priority queue. I hope I'm spelling this right. Which is going to be similar to the queue we had before, but now each state we put in is going to have an associated value with it. And that value is going to be the total cost we've seen thus far. And that total cost we've seen thus far we'll call G, which G can stand for like the gain, the amount we've gained so far from the start. And so we're going to pass in these pairs of a state and then the gain to that state, in which basically we're defining G of state to be pretty much the sum of all the costs going from the start to that current state, taken by some specific path. Like, this isn't like a formal like mathematical like definition of it, but there's just a way to think about it, right? You're taking the sum of all the costs on some path where you go from the start to the state that you're referring to. All right, so you'll see this as we go along through the example. And so, of course, always starting off at the start. Actually, let me just note down the expansion order. And so we're going to put into here A, and A has an associated cost of 0. So A gets moved to the front. And so we're going to take out, there's nothing else to put into the priority queue, and so we're going to take out our value here. And for this we'll just keep the value along with this, so I don't have to spend the time to erase it. And then we'll maybe just rewrite it afterwards. And so once we've expanded A, we see that we're going to put into here. Now we don't really care kind of the order that we put into the we put the states into here, because they will be ordered by their associated gains, that G, that by that G function, or like the cost they've added up so far. So from A, we have B, which has 0 plus 8, which is going to be cost of 8. And we have C, which has a cost of 0 plus 2, which is 2. So I just wrote them in the order that is correct. I'm going to put them to the front now. And so now, with nothing else to put into the priority queue, we're going to expand from C in where C has a value of 2. And so with that, what we'll put into here is E, because from C we can get to E. And now we have this 2 plus this 5 here, which means that E has a value of 7, which for the priority queue would put this in front of B, 8. And so now the next thing we will expand is E, actually. And so from E, we have F, which has a value of 2 plus 7, 9. And we also have G, which has a value of 7 plus 7, which is 14. So it looks like there's going to be a little bit of shifting here. So this is going to go in the front. We're going to need to put G14 in the back. Whoops, forgot the comma. And just like that. So now we've ordered this within our priority queue. And so now we are going to expand B. And so when we expand B, we can see that we have state D, which has a value of, we had 8 plus 5, which is 13. And it also has E, which E here has it's 8 plus 3, which is 11. And so now we're going to do a little bit of shifting. This G14 here, it's going to go towards the end. And then we have the order of 14, then 13, then 11, then 9. Yep, which means that, let me slide this over. The next value we're going to expand, or the next state I should say, we're going to expand is F, which has a value of 9. And we can see here that F isn't pointing to anything, and so we're simply just not going to add anything to the priority queue because there's nothing that's being added from F. And so then the next thing we expand is going to be E. And so from E11, what we're going to get here is we're going to get F with a value of 11 plus 2, which is 13. And let me actually first add everything before doing that. And we're also going to get G with the value of 11 plus 7, which is 18. Oops. Just a little bit weird because I remember seeing G before, but yeah, we're not particularly remembering the states that we visited before. which in that case we're doing a tree search. We aren't doing a graph search, in which a graph search you would be remembering the previous states that you visited. So yeah, we're just doing a tree search here. So this is 11 plus 7, which is 18. And so now here, this G is going to be more to the left. I'm going to slide over this F here. And in terms of the priority queue for when it comes to a tie, you can have it any way you like. You can take ties into account any way you want. We can just have it where it's in alphabetical order, and so then D would come before F. But you can also have it in terms of like whichever one was there first. But we'll have it in alphabetical order here. And so now for here, the next thing we would expand is D. So I'm going to put this below. So we have D13, and from D, we get G13 plus 9 is going to be 22, which is just going to go away at the end. And so you can see how like this is kind of ending up on like all the G's, right? Which is kind of like what we were doing before, in which we were seeing all the paths to G, and then we saw that, okay, the one with the least cost was actually 14, in which right now 14 is in the front in terms of our priority queue. But before we take that into account, because this is an uninformed search and we don't know if anything is after F, that's why F is here, and we need to expand this F, and by expanding it, there's nothing that comes after it, right? So we put nothing into the priority queue. And so then the next thing that we would expand here would be the G state. And from the G state, we would get to H, comma, 15. But now for the priority queue, it's going to be a little bit different in terms of when to get the goal state, because now that we're taking into account the cost, we don't just want to instantly get the goal state once we see it, but we want to make sure that the value we're getting to the goal state is the actual best cost. And so what we want to do is wait until, in terms of our priority queue, H is at the front here, so that then we can grab it and expand it. And once we expand it and we see that, okay, now we've expanded to a goal state, and so now we finish. Then we would be done. But now that I think about it, I don't know if from how we're expanding the lowest cost nodes first, if that would mean that once you expand to a goal state, that means you've already found the shortest path. But that might be something you guys might have to think about, because I can't confirm it off the top of my head. I would like to say that you don't have to do what I just said about like waiting until the goal state is in the priority queue and then you take it out from the front, but instead just kind of like if we had H15 before even putting it like into the priority queue, before even putting it into that, we can just say like is goal state similar as before, and if it's true, then we expand it, because obviously if we're expanding from the lowest cost first, then once we expand and get into a goal state, then we're good to go, right? But I mean, it might be the case in which you have maybe two goal states, like if you had like another goal state here, which you call like H2 or something like that, in which it costs like $10, then you might want to go to this goal state instead. So just something to think about. I can't. I mean, now with that final example, I think yeah, you should wait. You should not have the is close state function to check that within the priority queue, because at the same time you're only just kind of checking for one more check, so that your goal state and its associated gain would be at the front of the priority queue, and then you take that out. So yeah, that's how I would leave it off as. And so now, lastly, looking at the path order, what is the way you traverse this path? And so, of course, let's start from our ending here, h, which is 15. And so from here, what we're going to want to look at, let's see, it's going to be a bit different because we want to look at the costs now. And so yeah. So what we can see here, it's a little bit more complicated to see this, but we'll see that at the goal, we got a total cost of 15. And so looking to the left here, we see that G here has a cost of 14. And so if we see that the cost of where you're currently at subtracted by the cost it took from the parent to go to expand into the child node within this graph, then this would be the correct order to go to, which I guess will make a little bit more sense once we see it later. But essentially, we're going to start at H, and then we see that G here is 14, where 14 plus 1 is 15, or you can think of it as 15 minus 1 is 14. And so we, of course, are going to go to G. Now, from G here, we can't go to F, so we don't need to worry about that. If we look at D, D is 13 here. And if we look at E, we have to look at all the parents, or all like the nodes which, when expanded, equal output that node, in which for G would be D and E. So we have D here and we have E here. So D was 13 and E was 11. And so now looking at the paths, we can see we need to determine, okay, we know from G we go to H here. But now we need to determine, from D do we go to G, or from E did we go to G? And so we can see by the values from the expansion order, well, from D we had a total value of 13, but 13 plus 9 is not equal to 14. Similarly, 14 minus 9 is not equal to 13. So that means we did not go from D to G, but 14 minus 7 is not equal to 11 either. So now from there, we need to decide, like, what do we do now? Well, it means that there must be other values that we need to look at, right? And so for D, we can take that out. We can actually look at these one by one, and we can see that D is not a parent of, or we can see that D is a parent of G, but 14 minus 9 is not equal to 13, so we take that off. And for E, well, E is a parent of G, but it has a value of 11, but 14 minus 7 is not equal to 11. And so we take that off of our expansion order. Or not off the expansion order, but we don't account for it anymore for our path order. Next would be F, but F is not a parent of G. Next would be B, but B is not a parent of G. Next would be E. E is a parent of G, and it has a value of 7 now. And now we can see 14 minus 7 is equal to 7. And so now it's like, great, okay, now we found that the next value here is G. Or my bad. It's because I was underlining G. Next value is E. So we put E here. And now from E, we have 7. And now we look at C. Well, C is a parent of E and has an associated value of 2 within our expansion. And we can see that 7 minus 5 is equal to 2, which lines up. And so that means C must be a part of our path order 2. And now from C having a value of 2, we check A comma 0, we see 2 minus 2 is equal to 0, which means that A is a part of the path order 2. And since we've gone through the entire expansion order from back to start, and we finished on our start node, we started on the end node from the expansion order, and we went backwards to now finish at the start node, which was A. And now we finally got our path order, which is A to C to E to G and to H. And this is the most optimal path to take in terms of the cost, and for this case, the total cost would be 15 or $15 if you want to still treat this as the dollar problem where you're trying to get from A to H by spending the least amount of money. And so, yeah, that is everything we went over, or not entirely everything. There's a lot of like finer details, but I plan to go over that like within other like other videos that are maybe more like formal, of like a more formal teaching style in which I go through the book myself. But yeah, this is just kind of just an overview of what we went through for this week of class. So if you have any questions, feel free to leave them down below, and always feel free to rewatch the video, or if you felt like there was something that was not explained clearly, or something that you wish I explained and you wanted me to, I can maybe do in another video, or I can take into account. Let me know as well. But with that, thanks everyone for watching. Hopefully you learned something new, or hopefully this also clarified anything as well. And yeah, I'll see you guys next time. Bye-bye.